Have you ever wondered how all the little components inside your phone or your computer actually talk to each other? Well, today we're going to decode those secret conversations happening inside basically every piece of modern electronics you own.
Right? It's a really good question. You've got processors, sensors, memory, all these different parts that have to share information, and they have to do it without messing things up. The answer is that they use a set of rules, we call them protocols, that act like a common language. And today, we're going to explore the three most important ones: UART, I2C, and SPI.
So first up is UART. It stands for Universal Asynchronous Receiver Transmitter, which is a mouthful, I know. Just think of it as one of the oldest, most straightforward ways for chips to talk. It's the simple, reliable workhorse of the electronics world.
The best way to picture UART is like a direct phone call. It's just two chips connected directly with a dedicated point-to-point line. One chip talks, the other one listens. There's no fancy network stuff, just a simple, direct conversation.
Now, the key word with UART is asynchronous. All that means is there's no separate clock wire to keep the two chips perfectly in sync. Instead, they just agree on a speed beforehand. We call that the baud rate. And as you can see here, the setup is dead simple. One chip's transmit, or TX line, connects to the other's receive, or RX line, and they both share a common ground.
So how does the receiving chip know when to actually listen for data? Well, there are two main ways. The first is called polling mode. This is where the processor is basically asking over and over again, "Got anything for me? How about now? Now?" It's super easy to set up, but man, it wastes a ton of processing power. The smarter way is interrupt mode. Here, the processor goes off and does other things, and the UART hardware only gives it a little tap on the shoulder when new data has actually arrived. It's way more efficient, but it can get a little tricky if data starts flying in too fast.
And here's a classic tip from the engineer's notebook. If your UART communication is just coming out as garbage, the very first thing you should check is the baud rate. If one chip is talking at 9600 bits per second and the other is trying to listen at 11,520, it's like one person talking in slow motion while the other is listening on fast forward. It's just going to sound like noise. That mismatch is the #1 culprit almost every time.
Okay, so UART is perfect for a one-to-one chat. But let's be real, modern devices are more like a busy team meeting. What if you have a dozen different sensors that all need to report back to one main processor? That's not going to work with UART. And that is exactly where I2C, pronounced I2C, comes in. It's designed for this exact problem. It creates a little network, called a bus, where one main device, the master, can manage conversations with a whole bunch of other devices, which we call slaves.
And the real beauty of I2C is that it handles this whole network with just two wires. You've got a data line, called SDA, and a clock line, SCL. But wait, if everyone's sharing the same two wires, how does the master talk to just one specific sensor? Well, that's the brilliant part. Every single slave device on that bus has its own unique address. It's basically like giving each chip its own phone number on a party line. The master just dials up the address of the device it wants to talk to.
So, what does one of these conversations look like? When the master wants to send some data, it follows a pretty strict set of steps. First, it sends a start signal to get everyone's attention. Then, it broadcasts the specific address of the slave it wants, plus a little write signal. After that, it says which memory location it wants to write to, and then finally, it sends the actual data.
Now, after every single byte of data the master sends, the slave has a very important job. It pulls that data line low for just a split second. This is the acknowledge signal, or ACK. It's the slave's way of saying, "Yep, got that byte, I'm ready for the next one." That little bit of feedback is absolutely crucial for making sure the communication is reliable.
But what happens if the slave doesn't pull the line low? Well, that's a not acknowledge, or NAC. And here's the thing, it doesn't always mean a catastrophic error. It could just mean the slave is busy, or maybe it's not even connected, or if the master is reading data, a NAC can just be the slave's way of saying, "Hey, that's all the data I have for you." Understanding NACs is a huge piece of the debugging puzzle.
Okay, let's put you in the lab for a second. You've just wired up a brand new temperature sensor, you run your code, and crickets. Nothing. Your sensor just isn't responding. What's the very first thing you check?
First thing, triple check that slave address. It is so easy to misread it in the datasheet. Next, check your hardware. I2C needs something called pull-up resistors on both the data and clock lines to even work. And here's the pro tip. If you're getting a NAC right after you send the address, it almost always points to either a wiring problem or you've just got the wrong address.
So I2C is fantastic for managing a whole network of slower devices like sensors. But what if you need pure raw speed? What if you have to move a lot of data and you have to do it fast, like streaming video to a display or writing to an SD card?
This is where our third protocol, SPI, or Serial Peripheral Interface, really shines. It is built for speed, plain and simple, and it gets that speed by using more wires. You have a shared clock line and then two separate data lines, MASI, which stands for Master Out Slave In, that's for the master to send data, and MISO for Master In Slave Out, where the slave sends data back. Having two data lines means it's full duplex. Data can flow in both directions at the exact same time. The last wire is the chip select, which the master uses to tell one specific slave, "Hey you, I'm talking to you right now."
So, if I2C is like a conference call, you can think of SPI as a private, high-speed line from the boss straight to one employee. The boss uses that chip select line to get that one employee's attention, and then they can have a super fast, two-way conversation without anyone else on the network interrupting.
Of course, with all that speed come a few more things to look out for when things go wrong. A really common trip-up is the clock configuration, something called polarity and phase. Both the master and the slave have to agree on exactly how they're going to read that clock signal. Oh, and some devices, especially memory chips, have this weird quirk where you have to send them dummy bytes. Basically, you send useless data just to get the clock running before they'll start sending back the real data you actually want.
All right, we've met our three big contenders, the simple UART, the networked I2C, and the speedy SPI. Let's put them all side by side and see how they really stack up. This table really lays it all out. Choosing the right protocol is all about understanding these trade-offs. You know, for simple, direct communication or just for debugging, UART is your best friend. If you need to connect a whole bunch of sensors using the fewest wires possible, I2C is the undisputed champ. But when you absolutely need to move tons of data at the highest speed you can get, for things like screens or fast memory, you've got to bring in the power of SPI, even if it means using up a few more of your pins. So there you have it. UART, I2C, and SPI. These are the three fundamental languages that let all the tiny components inside our devices have all their complex little conversations.
And that's really the big takeaway here. Once you start to get how data moves through these buses, you start to see the digital world in a whole new way. You're not just a user anymore, you're starting to understand the fundamental dialogue that's happening just beneath the surface of everything.
You've basically been given the keys to unlock countless projects. You can read sensors, you can control displays, you can talk to almost any modern chip out there. So the only question left is, what are you going to build with it? What conversation are you going to start?